Yeah, sure.
All right, everybody, welcome to the first seminar of the winter semester this year. Today we have Kevin Wong presenting his master thesis work on developing a generative design framework for optimizing public transit network design. Kevin Wong is excited to begin his 2022 by completing his master's in civil engineering at University of Toronto and starting a new position as transportation planner at IBI Group. Having grown up geeking out over public transportation and being fascinated by applied mathematics, Kevin is fortunate to have the opportunities to channel his passion towards planning for an efficient, sustainable, and safe transportation system that prioritizes walking, rolling, and public transit. Kevin, the floor is all yours.
All right, good morning. Today I'm going to present what I've been working on for some time now. It is going to be a generative design framework for optimizing public transit network planning. This is basically really a workflow of sorts to using something called generative design, which I will introduce in a second, to optimally design network using more of a computational approach. But we'll begin talking about transit network planning and some of the challenges that are associated with it. So transit network planning, something that we have taken in Professor Sasharabi's course. As demand for transportation has become increasingly complex, transit planning has also become a very complicated task. Unlike, in the background, you see a transit map from 1924, where all you need to do is really to design routes from downtown to where people live and from people live to factories. These days, you have really different type of land uses distributed over very large areas. And you have a lot of trip purposes across, the city, across the region. You have population in urban and suburban regions continues to grow, and that generates a lot of different trips, and also a very limited amount of resources available to each transit operator. So really have to count every. Must say, transit network design. However, transit network come together through a series of three steps. So you have the strategic level, where you basically, in a sense, draw lines on a map, but it is slightly more complicated than that because you need to consider how each route interacts with the entire system. And you have what's called the tactical level. Tactical level is really the route operational characteristics. So for example, how many stops are on the route? Where are these stops? What kind of headways are you running on the route? Are you running any short turns? Are you running on any branches of the different side street? Where are your terminals, etc. So these are really route operating characteristics. And then you have the more general operational operational side, where you need to assign drivers, assign vehicles onto the route, compute travel times and so on. And for this particular study, we're really focusing on the first two stages. The first stage, when it comes to assigning drivers, assigning operators, there are a lot of algorithms that already does that, but we are really just focusing on how to generate these lines on the map and how to make sure that we have appropriate operational settings for them. Some of the big to solving what we call UT-NDP, that is the Urban Transit Network, and the TNDFSP, I'm sorry for all these acronyms, the Transit Network Design and Frequency Setting problem. I was just referring it to as the Transit Network Design problem from now on, just to make it easier. But some of the biggest obstacles, the first NP-hard problem. So for those who doesn't understand what this term means, basically means that you cannot solve this problem computationally in polynomial time, which means that as your size of your basic size of your problem increases, your problem becomes basically becomes unfeasible because you can't compute it in time, very likely because your computational time is going up exponentially. So that means that you can't really solve it by brute forcing it, by trying to plot every line available on the map. So a lot of mathematical methods that are really strong in theory, it doesn't apply here. Substantial data requirements and model requirements. So you do need a lot of data and model, to design transit networks, which we will touch on later. But a bigger challenge, even bigger challenge than that, is that you can't actually use all that data and model if your computational time is, that important to you. If you need to take care of computational time. Also, there are a lot of route attributes. We've talked about headways, we talked about stops. All of these things need to be optimized, and we need to consider things like where are the transit terminals, where are the depots, how many vehicles that you have. It's a big problem with a lot of intricacies. And then there's the fact that in most urban networks you actually have a large network with a lot of links and a lot of nodes. So all of that contributes to a very large problem, that is high computational costs, which is something that I ran into as I try to actually implement this framework. It's that computation become an obstacles, significant obstacles on its own. Now, a brief review of what has been done in the literature. There's actually quite a bit that has already been done in the literature. It starts with Pat's, this author in 1925, which introduced the first heuristic algorithm to generate transit network and try to come up with an optimal network design. But as you can imagine, at that time, there isn't really a lot of access to computers, and there really aren't a lot of good computational resources. And as this is an MP hop problem, it means that nobody is really able to compute it efficiently using just pen and paper. So there really isn't a lot of movement in this area, and all the way until 1980, where Mandel published his quite a landmark paper that introduced a two-stage heuristic algorithm that kind of generates routes based on kind of minimizing, based on minimizing transfers and kind of based on the demand that is available. And it also includes one of the most useful and most frequently used benchmark network, that is the Mendel 1980 network. It's based on a small Swiss town, and it has a demand matrix and as well as a small number of nodes and rope links. And it is a network that is most frequently used among all studies to kind of compare performance. Since then, there have been many types of models attempted. There are still some mathematical models, but all of them have a lot of simplifications. For example, one of the most common type of mathematical model is used is continuum approximation. That is basically you spread out the demand, instead of having discrete demand in each node, you spread it out kind of like a density, and then use, a kind of an integral approach to kind of optimize. You build up a mathematical model to kind of optimize kind of transit links. But that model has a lot of simplification, as we said, the biggest one being that it has a really strong assumption when it comes to demand, that it has to be able to fit a function, continuous function. And then you have heuristic algorithm. Heuristic algorithm are algorithms that are specifically designed to generate routes. So these are algorithms that really the author designed them specifically for the purpose of generating transit networks. So those algorithms can be very simple to understand. They can be efficient. But most importantly, they are easy to understand. They take advantage of things that planners have learned from their everyday experience when it comes to generating routes, how to improve the network, what kind of modification at each step to do to be able to improve the network that way. Those are really, you really need to have a profound understanding and to some extent some luck to be able to come up with an efficient heuristic optimization program. Meta heuristics, on the other hand, is not specifically designed for transit networks, because they are really just optimization methods that have been widely studied and understood in computer science and mathematical optimization. Things like genetic algorithms, simulating annealing, taboo search, swarm-based optimization, bee colony, ant colony, for example, etc., etc. So these algorithms has been Well, research, there's been a significant amount of literature. There has been so many variation that you can ever imagine. You can also integrate them into, different, you can combine them together. There's so many literature out there. Whatever versions of it that you want, there's definitely someone in comp sci that has already done it. These algorithms, they are not specifically catered to one transient network design, so you do need to incorporate elements, for example, graphical elements. The fact that transient network is a graph, you need to put into that. But other than that, these algorithms are very well understood, especially their strengths and weaknesses and how, what kind of issues they run into when it comes to, searching a giant and complicated search space. So that's why meta heuristics is actually some of the most commonly used model, in particular in this area. But what are some of the needs for improvement? Why do we need to do this if there are already so much literature in this field? First of all, most important of all, we need faster algorithms and faster workflows in general. There's always a need to be able to go faster because we have such complex networks and we have so many data. We have so much data that there's always a need to to be able to speed up our workflow. Also, another important thing is that there's a need for a more diversity of solution. So most studies in the past tend to generate a single solution or one or two solutions that look very similar. But in reality, a transient planner may be looking for a more variety of solutions to try different things. Also, most models build on a lot of assumptions. For example, a lot of past studies build on assumptions that demand matrix fixed. The transient demand matrix is fixed. That makes things a lot easier, but it also means that you, as your network changes and mutates, you get a more unrealistic. It becomes more unrealistic compared to the demand. The demand doesn't really apply that way anymore. And we want to be able to solve real-world cases in reasonable times. So that brings us to generative design. An example. So what is generative design? You might be wondering, and I really like to give this example that I even wrote about it earlier. Wrote about it when I first actually learned about generative design. It is the example of trying out clothes and how to layer it on in the winter. So, for example, you want to go out and it is winter, it's cold out, and you want to be able to, dress yourself up. So, what would you do? So I would, try on different layers. I would try on my jacket, I would try on my shirt, and then I would try on my inner shirt, and I would, and then after, I try on a few layers, I will walk out and I will see if it is warm enough. If it's not, I will come back home and I will, maybe swap one layer that I don't think is working well enough, and then I will replace it with another layer, and I will repeatedly do that until, well, I walked out my door and I feel like, oh, I'm warm enough. That's when I stop. And sometimes I will be able to generate multiple outfits because I do have a combination of shirts and inner layers and pants, and etc. So I will be able to generate multiple outfits. All of them will be maybe functional to the weather and the temperature that I have having that day. So I'll have multiple choices, but they might have different trade-off. For example, some might look more casual, some might be more easy for walking around. But that is generative design in a nutshell. It is really to try out different things, generate a ton of example, and then hopefully at each step of the generation, you're moving towards a better example. And that is what a generative generation model that needs to do. And at the end of the day, you arrive at multiple solutions. You have a choice of multiple solutions. That is also an important part as well, because that gives you the flexibility to adapt as you may, to apply it towards a specific application or specific intent. So generative design can be generally divided into 5 steps. First of all, you define the problem. You make sure that you have your objectives, you have your constraints, standard optimization stuff. But you also want to be able to define your reference design. So you need to be able to have some starting point, as well as performance requirements, making sure that you need to be able to hold what is the desired performance of the solution. So what is the desired attributes of the transient network? You need to be able to generate a new design. That is a significant part. You need to be able to evaluate. That is also significant, but in a sense that, the computational part is, you need to be efficient, and then you want to be able to validate that solution, and then you report. It is very standard optimization stuff. There is one, aspect on the top. You can see the word designerism on the top, kind of links to all the steps. That's because generative design is supposed to, that is quite automated, but at the same time, the designer is supposed to kind of monitor each step, to step in and make adjustment at real time, and that is because as you generate new solutions, the designer is supposed to be able to kind of make changes, make mutations to improve whether it's an initial solution or your generation workflow, how you're generating the network. That is how you kind of improve. That is part of how you are improving the process, because you need to step in real time to see if the transient network that you're generating is actually getting better, or if it's actually usable in real time. So in particular, Khan and Wong, it's 5 different attributes that are important for an effective generative design methods. First of all, you need to have a search and generation strategy that is effective, that you can generate optimal and hopefully globally optimal solution in your solution space. You need to be able to autonomously set up a viable design space for a given model. So you really need to define the problem well. Be able to work with both continuous and discrete design parameters. That is very important. Be able to create uniformly distributed and variant design from the entire design space. And that is what I allude to when I say that we want to be able to generate a variety of design. This is kind of a breadth first search scenario where you really want to explore the search space instead of diving straight into the grid based, for example, transient network, or the hub and spoke network that we have known very well. And you also want to be able to have the ability to explore effectively both the constrained and the unconstrained design space. So when it comes to design generation methods, there are typically 4 types of design generation methods. And design generation methods, to remind yourself, is this step. It is one of the most important steps because well, part of it because we are talking about generative design, so it's the name, but also being able to generate the solution is what makes this framework important. So there are 4 types of design generation methods in general. There are parametric modeling, so that is you have a mathematical model, you're basically changing parameters to be able to optimize it. That's the most typical type of optimization models out there. But with transient networks, it doesn't really apply because we've talked about how it's NP hard and it's generally just really difficult mathematical models. Topological optimization. So you have gradient descent and such. These are kind of models that could supplement what we're going to talk about next. But topological graph optimization also aren't really that useful in our sense. That brings us to evolutionary optimization and data-driven methods. Evolutionary optimization, in any sense, basically are equivalent to meta-heuristic methods that we've talked about a little bit earlier. So genetic algorithm, simulated annealing, taboo searching, etc. So basically, evolutionary means that you are moving towards a better solution. You are evolving towards a better solution over time. So that's the hope. And being meta-heuristics, it means that it can solve these NP-hard solutions by providing approximately optimal solutions, by generating them. Data-driven methods, on the other hand, are things like machine learning, AI, etc. So you're basically using things like neural network or some kind of models to be able to a variety of models to be able to kind of generate solutions by really throwing it into a black box and hoping that you will get something out. That is actually, there are different methods actually haven't really been well researched into transient network planning. It is a big regret of mine over this project, really big one, because I've certainly tried and experimented on it, but I haven't had the time to be able to figure it out. But it's a big regret, I must say. But it is certainly I have believed that I'm strongly believe that this is something that could be applied, especially towards part of the problem. But now we need to move on to defining the problem. I'll go through all of this pretty quickly. Problem definition of the objectives. So we're going through a version of the problem that is defined in my paper, but each paper will define it differently depending on their data resources and the planner's priorities. But to me, the key problem with transit network planning is really two things: minimizing all travelers' generalized costs and minimize transit operators' capital and operational costs. So this obviously includes travel times for all travelers and costs, money that they pay, as well as all the kind of vehicle and drivers costs, etc. for transit operators. So the reason why I only chose these two, first of all, is that if the more objectives that you have, the more dimensions that you have, the more complicated your optimization algorithm is going to run into. But at the same time, these two are really the core of core issues with transit network planning. The two big trade-off, as you may say, either you want better service, but it comes at a higher cost, or the transit operator want to save costs, but it kind of affects the passengers. So these two are really the main trade-off when it comes to transit network design. And instead of combining them into a single function, the most effective way that I believe to be able to do it is construct something called a Pareto optimum curve on right, something that most of us probably have seen before. Because combining them into a single function prevents you from adding additional variable. It also prevents you to understanding the trade-off between the two objectives. So this is kind of the best practice to use Pareto optimum curves. So as for the problem definitions, again, when it comes to constraints, there is possible to have more, but I believe these are kind of the essence of the key to define a transit network design problem. It must be a connected network. It must be within some walking distance from each other. So that's the coverage requirement, and then a maximum transfer requirement, as well as from rapid transit services, as well as kind of a network robustness criteria. That's how your network reacts in the case of a disruption. As well as a route-based kind of constraints, for example, maximum and minimum route length to ensure that you don't plan routes that are either too long or unusable because they're too short. Minimum headways, directness, that's something that may or may not be useful depending on really your network structure. There are times where you have routes that are just not as direct as they should be, but that is an issue. Route utilization, that comes from the transit assignment model to see, how well or badly your route is being utilized, and each route must connect to one other route. This is equivalent to the connected network requirement, because if each route is connected to one other route, not equivalent actually, but similar. If each location is served by a route, and each route is connected, your network is connected. Inputs, and that's what I talked about earlier. What part of why the computational cost of this problem is so significant. So you need to start with a road network. Ideally, you have a travel demand model, or otherwise you'll be using fixed demand. And with a travel demand model comes with a mode choice model, and then also a transit assignment model. And these three, the big four models tend to take up a lot of time in computation if you're running that many iterations. Ideally, you have a transit cost, a capital operational cost models to be able to calculate what the cost of what the transit operator is doing. In some cases, some studies have also used number of vehicles or number of service hours, for example, as a proxy. That's also possible. Pedestrian network, that is supposedly important if you actually want to plan a quality transit network, but it's not something that a lot of studies has access to, especially not in this one because of time constraints. Transit infrastructure network, if that exists, things like rail and trolley wires, and transit depot and transit terminal, and hopefully you have a version of the existing transit network. But if not, we'll briefly touch on initial solutions later on, routes, frequency, and stops, and so on. There are also a variety of issues with designing the methods itself. So really the core of, how to come up with a generative design methods, starting with initial solutions. Initial solutions is an important part of every optimization problem. If you want to get a good result at the end, you need to start it off good. There are various ways to generate optimization problems. First of all, you can start with your initial network, the network that you already have. But you can also, using human and as well as, simpler optimization programs to generate a variety of network that allows you to more likely to exhaust your search space. Choice of design generating model, that is really, at this point, is kind of a more of a personal preference. Meta review has shown that, there are a lot of variety of meta heuristic models that do outperform the benchmark, the classic genetic algorithm model, but the performance isn't that, the difference isn't that significant. There's definitely improvements there, especially when it comes to, depends on, the objectives that you have, but depends on our objectives as well as the size of the network. But, there hasn't really been very significant improvements based on the literature review that I've read, and as well as based on all the literature I've experienced, as well as the, but also there isn't a lot of effective comparisons in the literature so far, to be honest. Dividing a problem into layers. This is a problem, that is best divided and conquered. So transient network design and frequency settings are two separate problems that are very much interconnected. So it is possible to divide it into different layers, tackle it with different generation solutions. For example, there are some algorithms that use genetic algorithm for network design, and then use taboo search for frequency optimization. It is also possible to use different types of methods. For example, maybe a genetic algorithm for network design and a machine learning method for frequency optimization, and then you kind of use a feedback loop to make sure that you're constantly updating your either your network or your frequency with your newer frequency and network. Parameter setting. Setting parameters is difficult. But again, you can use all kind of optimization methods, machine learning that can do that. Computational challenges, it's always a big one. I can't remember what I list this point here for, because we've talked about computational challenges quite a bit already. Room for human feedback. That is where you should always consider implementing kind of gaps or implementing space for yourself to kind of, or myself in this case, to be able to, actually to understand, what's going on inside the algorithm, what kind of results are you generating, and to be able to, make modification of it in real time. So this is the overall framework of generative design transient optimization models. You start from the input, you start from the, given the initial solutions, you come up with a generation model. In the generation model, there's strategic part, and there's also a tactical part that makes sure that, you're really, the strategic part is you generate the network, you feed it into your generation of your service, that is your frequency, and in some cases, you might also consider short turns and stops and so on. And so that, and we should consider an internal filter. So that means that filtering your network filtering network based on your network objectives before you move into the tactical generation part, before you even move into future constraints, and that will save on operational costs. And also, it is possible to consider an iterations here internally inside the generation model, so that you're optimizing your generator optimized well enough before it goes into tracking your constraints, evaluating your objectives, and then checking it against your set performance targets, whether or not the network is performing well enough already, or the number of iterations has been reached. And the planner is kind of monitoring all the steps at all time to making sure that the generation model is performing well. So as generation model is generating a network that is feasible and applicable, the initial solutions works well, as well as at the end, it manually kind of validates the solutions I generated. And then at the end, you really look at should look at the Pareto criteria and select a preferred solution. So other applications, so besides all of that, other applications besides network design, for example, you want to, reduce service and increase service, which is what transit agencies have been doing across Canada recently due to COVID-19. So, if you want to change your number of vehicle constraints, but you don't want to modify routes, so that's an algorithm. This is an algorithm that is, applicable to that. Things like service patterns, so optimizing the service pattern of each route to make sure that you're really putting the service into use, as well as redesigning individual routes to coordinate with a rapid transit line. You might be able to you're able to fix certain routes, change a series of routes. That's also an applicable situation. So there isn't an implementation part presented here. I did do experiments especially with Mandel's network, but I wasn't able to kind of obtain very good results on bigger networks not because of the issues with this framework, really because of my implementation and my time issues. But overall, the next step, one important step, will be implement this generative design framework for UT-NDP and TNDFSP. We want to compare performance across existing heuristics and meta heuristics algorithm. Ideally, we would be, really designing different design generation methods and then compare it using the same network, which is something that is seriously lacking in existing literature. Something I really would regret not being able to do. Consider the potential of using machine learning, artificial intelligence. I really love machine learning, artificial intelligence, again, a big regret of mine. Pursue methods that cut down on computational cost and time, and sensitivity analysis, always important, always lacking. I've been rushing a little bit and we have a late start, but I'm hoping that I will take your questions if you still have any. Because this is more of a general kind of a framework check, as I would say. It's not, it lacks I understand that it does lack an implementation because I wasn't really able to get to a really good implementation in time for the thesis. So, but I still hope to be able to answer your questions, kind of a more theoretical aspects of this framework.